We'll now look at weak base equilibria. A weak base is any conjugate base of a weak acid. The conjugate bases of strong acids, such as chloride or iodide, are too weak to even react with water in aqueous solution, so we don't even consider those. Most weak bases are amines or derivatives of ammonia. Some have special names like pyridine. There's aniline, and this, just by the IUPAC name, has to be methyl from the CH3 group, methylamine. So most of them look like ammonia, and most of them behave like ammonia. That is, in the case of, let's say, methylamine, you have nitrogen with a lone pair of electrons, 2 hydrogens, and then the methyl group, CH3. And in water, about 3 out of every 100 of these molecules at equilibrium will have attracted away from water the hydrogen nucleus, or the proton, or the H plus ion, thereby causing this bond to break and the NH covalent bond to form, thereby generating hydroxide. And in this case, from methylamine, we call the cation methylammonium, the conjugate acid of methylamine. The conjugate acid of aniline, for example, would be anilinium cation, and the conjugate acid of pyridine would be pyridinium cation. So usually the name of the acid compared to the base will either end in inium or onium. Other conjugate bases of weak acids: the weak acid nitrous acid has its conjugate base of nitrite. Hypochlorous acid has a conjugate base hypochlorite. As you can see, these are pretty much all anions. Hydrogen sulfite has a conjugate base of sulfite, and hydrogen phosphate anion has a conjugate base of phosphate. Okay, so 2 examples of these weak bases reacting with water: an organic example and an inorganic example. Aniline reacts with water, again taking the H plus from the water, making it an H plus acceptor, and that's what bases do. So aniline forms its conjugate acid anilinium cation and generates hydroxide, which is why the pOH goes down and the pH goes up in these basic solutions. Again, these are weak bases, so at equilibrium the forward reaction doesn't appreciably occur that much compared to the reverse reaction. For an inorganic example, you have hypochlorite that gains an H plus from water and becomes hypochlorous acid, unionized, and generates hydroxide. So even though an acid is generated on the product side, don't think that you're going to form an acidic solution. You have generated hydroxide by virtue of the weak base reacting with water. So they form basic solutions. Further, there's no such thing as a container or bottle or jar of hypochlorite anions. They would repel each other out of the bottle. These weak bases come from salts, generally. The sodium cation is inert, as are all group 1 cations. They're essentially conjugate, quote-unquote, acids of strong bases: sodium hydroxide, potassium hydroxide, lithium hydroxide. So they are far too weak. They're just weak in name only. They don't do anything with water. So all group 1 cations, and of course calcium, strontium, and barium from group 2 are inert. So you can use any of those as the cations in the salt as your source of the weak base. Very generally or generically, you're going to have some kind of base, either an anion or an organic base, reacting with water, and it gains an H plus from the water and becomes its conjugate acid and generates hydroxide. So you'd have a K expression, an equilibrium constant expression for a given base B, of the conjugate acid and hydroxide concentrations at equilibrium in the numerator and the base concentration at equilibrium in the denominator. And water again doesn't show up because it's a liquid, and pure liquids and solids do not appreciably change in concentration at a given temperature. So if I wanted to write the equilibrium constant expression for hypochlorite anion weak base, that would be hypochlorous acid, that would be the product, one of the products, and hydroxide concentrations at equilibrium divided by the concentration of hypochlorite ion at equilibrium, which is usually going to be very close to the initial concentration for any kind of appreciably concentrated sample. Why is that? Well, these are weak bases, so they do not appreciably ionize or react with water. Now we'll look at an example, another equilibrium problem in which we can use an organizer to determine whatever is required from the given information. Very typically there's one extra step to these problems. We're to determine the pH of a 0.250 molar aqueous sodium nitrite sample. So nitrite is the weak base that we recognize. Sodium cation is inert, so that will not show up in the equilibrium net ionic expression. But notice they're not giving any information directly about nitrite. They give you the pKa of the conjugate acid of nitrite, which is nitrous acid, at a given temperature, and they're saying that it's 3.39. So you take that information and the relationship in aqueous solutions that the pKb of the conjugate plus the pKa of its conjugate has to add up to 14. So the pKb of nitrite is going to be 14 minus the pKa of its conjugate. So that's a easy calculation. 14 minus 3.39, and that will get us 10.61. And then by definition we can get the Kb value for nitrite is just 10 to the negative 10.61, and we'll leave it at that. There's no need to write that in scientific notation. Now we'll set that equal to an expression by writing the chemical reaction that occurs between this weak base and water, forming its conjugate acid. And you can see from the value of the equilibrium constant for this base that this is going to occur at a very, very low percentage. 10 to the minus 10 is going to be the ratio in that expression. So we'll put products over reactants to their coefficients. Nitrous acid, hydroxide, water doesn't show up, and nitrite. And again, that's at equilibrium. So this ratio is on the order of 1/10 billionth, so very, very, very weak base. But that's okay, it's going to generate an answer as far as the pH. We'll get that first by figuring out the pOH. So we'll set up a quick organizer here. We're given an initial concentration of sodium nitrite, and it's pretty intuitive or simple to figure out that if you have 0.250 molar NaNO2 and there's 1 mole of nitrite anions per mole of sodium nitrite dissolved, the moles cancel. We see that we get the same concentration of nitrite. So I'll put that right in there. The organizer, we have effectively about 0 hydroxide, 10 to the minus 7 molar from the water. That'll come out in the equilibrium line, and we'll put 0.250 molar for the nitrite. So 1 to 1 to 1 stoichiometric ratio. So minus 1x plus x plus x, that'll be the stoichiometric change. And at equilibrium, we just add the initial and the change lines. So we get xx and 0.250 minus x molar. We put those expressions, or variables rather, into the equilibrium constant expression. Kb for nitrite, 10 to the negative 10.61 is nitrous acid concentration, hydroxide concentration, 0.250 minus x. Because this is a very small number relative to this, in other words, initial concentration of nitrite is much, much greater, or it's greater than 1,000 times the equilibrium constant value, we can neglect the relative to 0.250, this amount. Even if we couldn't neglect that and didn't know any better, we can always check our answer at the end. If we end up getting an x value of 0.225, clearly that is not and was not negligible. But this certainly makes the calculation a lot simpler. We now cross multiply 0.250 times 10 to the negative 10.61 equals x squared, and therefore x, let's not forget what that is, that's concentration of hydroxide. At equilibrium, it's also the concentration of nitrous acid, but we're focusing on the hydroxide here, is the square root of, I'll write 0.250 is 2.50 times 10 to the minus 1 times 10 to the negative 10.61. So inside that square root is something on the order of 10 to the minus 10, we'll say, so we expect a concentration of hydroxide at equilibrium on the order of around 10 to the minus 5 molar, but at this point we can use a calculator. If this were a multiple choice question, we'd already have good enough approximation to get the answer right among the choices. So with the calculator, we get an answer of concentration of hydroxide at equilibrium is 2.48 times 10 to the minus 6 molar. And we could check that here, 0.250 minus 0.0000248, indeed that is a negligible quantity compared to that initial concentration of nitrite, which was 0.250 molar. Negligible. So now we can get the POH and then the pH. For the POH, by definition, it's the negative log of the hydroxide concentration, 2.48 times 10 to the minus 6 molar, and that yields 5.61, giving a pH at 298 Kelvin in aqueous solution. It's 14.00 minus the POH. As expected, we get a basic pH for this weak base. Not very basic, but somewhat. And that is 8.39. We see from the values that we got that there's very little reaction or ionization of water. We can get the percent ionization of water by nitrite. At this concentration, we'll just take the concentration of either product. We'll use hydroxide at equilibrium relative to the initial concentration of nitrite. That's the part over whole. And changing that to a percent, we just multiply by 100 and put on the symbol. So 2.48 times 10 to the minus 6 molar over 0.250 molar times 100. Very small number. 9.92 times 10 to the minus 4%. So practically no ionization, very little bit, but enough to keep the pH from being 7. It's slightly basic, 8.39. So for weak base problems, keep in mind that they can give you information about the conjugate acid, and you'll have to work your way over to the information about the conjugate base. Of course, they could do the same thing for weak acid problems, give you pKb values of conjugate bases. The other common permutation is that they'll give you an initial concentration of your weak base and the concentrations at equilibrium, or a means to get that information, and ask you to figure out the Kb or the pKb of that particular base.